when most of us think about the word desalination, I imagine that what first comes to mind is something like this. A large-scale mega facility, probably somewhere in the Middle East, treating hundreds of millions of gallons a year. And it's true. There are lots and lots of desalination facilities up and down the coast of Israel, for instance. In fact, Israel will soon have about 80% of their freshwater supply provided by coastal desalination. So there's really a mature technology here capable of delivering very, very large quantities of fresh drinking water. But there's also desalination across the US. Up and down the California coast, the Texas coast, and the Florida coast, there are about 20 desalination facilities, the largest of which is the Carlsbad desalination facility in San Diego. And desalinated water in the US tends to be used very differently than it's used in the Middle East. It tends to be used as a marginal water supply. So instead of accounting for 80% of the water supply portfolio, it's more like 8%. Why do we build these plants? We build them because they are drought-proof. They help us maintain resilient water supply portfolios, but also because they cap the costs that cities have to pay for water on the open market. I would say that these two examples kind of beg the question about whether desalination is relevant beyond wealthy coastal communities. And the argument that I want to make to you today is that we should think about desalination as a unit process, as a technology that allows us to tap a whole host of non-traditional water sources that we haven't used in the past. And to understand why we need to use this much broader range of water sources, I want to take a step back and sort of introduce you to the water system as a whole. Today's water supply is really built around four things. The first is ample fresh water. The second is extensive conveyance. We move water very long distances. We treat that water in centralized facilities. Those are typically very large centralized facilities. And then we discharge our wastewater back into the environment. And this linear water system has served us very well in the 20th century. It has historically delivered very low-cost, very resilient water supplies. But that system is also under a lot of stress. It's under stress because of climate change, stress on the supply side. It's also under a lot of stress on the demand side. So things like population growth and new water demands that are likely to grow in a decarbonized economy. And then it's under stress from things like emerging contaminants that we need to remove from that water supply and aging infrastructure. Most of our water infrastructure was built 50 years ago. It's now really in need of a refresh. And so given these stressors, people are increasingly turning to non-traditional water supplies. Water supplies that have either historically been ignored, like brackish water sources, or are currently considered waste, things like municipal, industrial, or agricultural discharge. And what I want to suggest to you is that tapping those non-traditional water sources is going to require new forms of treatment, including water desalination. You might ask, okay, well, that's great. You have all these new sources, but isn't desalination costly, and isn't it energy intensive? I'd say, well, it depends. The energy intensity of desalination is a direct function of the salinity of the water that you are bringing into the plant. So the lower salinity, the lower energy intensity, the higher salinity, the higher energy intensity. And we can see this in facilities today. On the x-axis, I have the salinity of your feed water for common non-traditional water sources. And on the y-axis, I have the average energy intensity across US facilities. And what you see is that expected trend where at lower salinities, you have low energy intensities, and higher salinity feed streams, you have higher energy intensities. But this plot actually gets a lot more interesting when you normalize it to the thermodynamic minimum of separation for these specific feed waters. And if you do that, you get a plot that looks like this. That seawater desalination data point suggests that we're actually pretty close to the thermodynamic minimum. And a recent plant that just opened in Saudi Arabia is treating seawater at $400 an acre foot and exactly 2x the thermodynamic limit. That is the most efficient industrial process that exists today. So there's not a lot of innovation opportunity right there. Instead, I think we, as a community, should be focusing on these waters at lower salinities, where there's an especially large opportunity for reducing both cost and energy intensity. The other thing that is important to understand, especially about municipal water supplies, is that the costs and energy intensity of water conveyance actually dominate those of advanced water treatment in most cases. So this is a picture at the Hyperion wastewater treatment plant in LA. LA is currently retrofitting that facility to recycle 100% of that wastewater. And it's going to cost them about $8 billion to do that upgrade and develop infrastructure to both treat and convey that treated water to injection sites on the other side of the county. 75% of the total CapEx of that project is in building pipelines for conveyance. So there's these very large OpEx costs associated with large-scale systems dependent on conveyance. There's also routine operational costs. And our group has done a lot of work to try to quantify just how much energy is involved in conveying water around US and other municipal systems. And so we developed a model that helps us look at a citywide scale at what the marginal energy intensity is of delivering water to end users throughout the system. And so you see these kinds of cumulative density functions that allow us to look at the whole range of users. That far, let's see, do I have I don't have any pointer, but the far right-hand side is the net energy of delivering water to users around a city. And in the blue lines, we've broken down that energy into treatment, or I should say transmission, or bringing water from the source to the treatment plant, the treatment, which is way on the left, and then the distribution. And so the takeaway from this is that 80% of the energy intensity of delivering most water is bound up in transmission and distribution. The other takeaway here is that if we could do premise scale reuse that was actually pretty inefficient, pretty energy inefficient, let's say it took a kilowatt hour per cubic meter to do that water reuse. In most cases, you would see a net reduction in the total amount of energy used to treat water. So, given that, we formulated a set of hypotheses which really suggested that we could most effectively reduce the cost and energy intensity of delivering non-traditional waters if we were able to build small-scale distributed desalination facilities. And to understand why, it's kind of helpful to think about why we build plants at the size we build them today. What you see here is the cost of water transport and treatment as a function of operational scale. And you immediately notice that your transport costs rise exponentially. This is because you're pumping water all over the place. But we tend to build plants kind of in this higher range because we have these economies of scale of water treatment. And so what we've proposed is that one way to avoid or kind of evolve the system is to replace those economies of scale in treatment with economies of scale in manufacturing, basically reducing the costs of water, of small-scale water treatment through modular appliance-like devices that might be present at the home scale, the building scale, or in modular trailers. And in effect, shifting this whole curve down and over to the left. We took this hypothesis to the US Department of Energy and said, you know, we'd really love to get some funding to develop technologies that enabled cost-effective distributed water treatment and reuse, and were awarded a energy water desalination hub that is called the National Alliance for Water Innovation. I serve as the research director for that hub, and the mission is to secure water supply through energy efficient and cost-effective distributed water desalination and reuse. We think about a whole host of non-traditional water sources, brackish water, seawater at the small scale, but also have a very heavy focus on industrial, municipal, and agricultural reuse. We also did a lot of technology road mapping to better understand what are the key technology challenges to help us deliver desalination at small scales that is cost effective and energy efficient, and came up with what we call A prime, or our 6 challenge areas. I do work in some of these areas, and I wanted to highlight just a couple of projects before I close. The kind of use-inspired research and technology development that happens in my lab spans many, many, many length scales, from the materials to the process, all the way up to kind of system innovations to help deliver these small-scale systems. We've made great use of our facilities up the hill at SLAC, specifically SSRL, to make some of the first measurements of concentration polarization in operando in membrane systems. We've used those in collaboration with a set of computational fluid dynamic models to solve the inverse problem of how do we design efficient spacers to facilitate mass and heat transfer in the modules that are used for water desalination. We've done a tremendous amount of work on new process design and optimization, exploring not only ways to more efficiently treat new types of water, but also to valorize some of the constituents that we're pulling out of water, and have a very interesting project right now thinking about how to generate precursors for low carbon cements. And then we've piloted a lot of these facilities. We've gone out to places to actually deploy these new technologies and see how they perform. And I'm blessed with a tremendous number of Stanford and SLAC collaborators that help execute on these projects, as well as a series of companies and utilities that have worked very closely with our group. The second thing that my lab spends a lot of time doing is water systems analysis and control tool development. So we spend a lot of time both building tools for our community to use broadly, and then using those tools internally to prioritize where we need new R&D development. There are 3 tools I want to highlight today. The first is called Water TAP, or the Water Techno-Economic Assessment Platform. This is an equation-oriented process systems engineering model that allows us to really optimize and explore cost-optimal system designs. We can think about this as an Aspen equivalent for water, except that we use state-of-the-art optimization approaches instead of optimization approaches from the past century. So we're really excited about that, and are really hoping to commercialize this through the hub. The second is a set of tools that we call FlexWater that help us evaluate opportunities for shifting the time at which energy is consumed at water treatment facilities or in water assets. And in effect, we're trying to move electricity consumption out of high cost times of use for electricity and into lower time of use periods. So we're deploying that both in water distribution systems, at water desalination facilities at Santa Barbara, and in wastewater facilities here in Redwood City, Silicon Valley Clean Water wastewater treatment facility. And then the final set of tools that we really work on developing fall under an umbrella of asking questions about where, when, and how should we optimally deploy these non-traditional resources to help secure water supplies at the municipal level. So you can think about these as capacity expansion models of sorts, and we are really thinking about adaptation both to future climate scenarios, but also future demand scenarios under a range of different options for future technologies. And so with that, I just want to close. Thank both my group of students, who's amazing, a broader set of collaborators across the country that contribute to the National Alliance for Water Innovation's mission, and all of the collaborators that I mentioned earlier.